nice place to be for a week. Okay, so my talk is about GLM, so generalized Lagrangian mean. So we've seen a bit of that, and we also have seen various related theories, for instance, in Paola's talks. And the idea here is to use differential geometry to, well, make GLM simpler, or at least somewhat different. I'll leave you to judge whether it's simpler or not. And this is joint work with Andrew Gilbert in Exeter. Okay, so what we've seen already is that in GFD there is this passion for splitting things between mean flows and perturbation waves or small-scale turbulence. So the typical things are, for instance, so this is a well-known picture from a paper by Dazzaro and others, which shows the motion of drifters after the passage of a storm. And so the noticeable thing is that there is a drift, which is rather slow, and there is also those fast inertial oscillations. So there's an example of a timescale separation where it makes sense to try to want to separate between the waves and the mean flow. This is a picture which Raf showed this morning, where we have now agreed that there is as much energy in this half and there is in this half. So this is the frequency spectrum at two different depths, I believe, in the ocean, showing that there is significant power at high frequencies, at the inertial frequency, at the tidal frequency. And again, it makes sense, taking advantage of this little gap in the spectrum, to try to separate between waves and flows. And then this is something which you may have seen, or something similar in Ted Shepard's various lectures. This shows the zonal mean circulation, meridional circulation in the atmosphere. So Paola talked about the Hadley cell, but it's also to show that there are higher. There's also a cell higher up in the mesosphere, the Breuer-Dobson cell. Okay, and again, so there is a separation between zonally averaged motion and then fluctuations in the in the zonal direction. Okay, so just as a motivation, I think you've seen enough means so far. So what this has led to is various people trying to develop theories to separate mean flows and waves or perturbations. And of course, the interest is when the waves exert some sort of feedback on the flow. So you want to be able to quantify that. So there's a family of wave mean flow theories which have been developed, and I've tried to list here what is desirable for such theories. So the first is that we would like to get some sort of reasonably simple equation for the mean flow. And we've seen that in the thickness averaged equations, for instance, where the aim was to get something reasonably good looking. Those equations for the mean flow should include the wave feedback in a form that can be parametrized. Now, it's also desirable that the mean flow track the real motion of particles, because, for instance, we're interested in heat transport, and that follows particles. And then this is maybe the angle of this talk is also we'd like this equation to preserve some sort of geometric structure which the fluid models have at the outset. So, for instance, what I mean by geometric structure are things like conservation laws of vorticity or potential vorticity, energy conservation, maybe things like wave action. Okay, so we'd like our models to satisfy that. And also, and this is behind GLM, it is good if you can derive at once a system of equations which is valid in many different regimes. So, which you can apply when you have timescale separation, or you can apply to a zonal mean, different contexts, different scaling. You can, of course, in each case, work out the equations using a small parameter, for instance. The idea of GLM is that you try to work in a non-perturbative way. So you don't have a small parameter at the outset. You try to derive equations which are valid at order 1. Okay, so a remark here is that if you have a mean flow which tracks particle motion, and if it also preserves potential vorticity conservation, and you believe that your mean flow is balanced, then having those two properties, 3 and 4, tracking particle motion, preserving potential vorticity, then you have a very simple governing equation, because that's going to be controlled by potential vorticity conservation following the mean flow, because it follows particles. Okay, so that's the kind of underlying principle of GLM. Okay, so the easiest mean flow is, of course, the Eulerian mean flow, where you just look at a particular location and you average your field there. And so this is just to kind of explain a bit better the point which Oliver Bühler made, that even in a simple linear wave field, particles don't simply have closed orbits, but they kind of drift with a velocity which is the Stokes drift. Right? So this is the simplest example. You take a velocity field which is small amplitude and is periodic in time and has zero mean. Okay, so the mean here will be periodic. So the Eulerian velocity field, which you obtain by just fixing x and averaging, is going to be zero. Nonetheless, particle motion is non-trivial. So you see that by solving x dot is equal to u of x, the idea is that this is going to be nonlinear, right? Because u is nonlinear. So if you just expand x in an x0, perturbation toward epsilon, perturbation toward epsilon square, you stick everything in x dot equals u of x. Here it is, so that's the x dot. So I start with a fixed center, if you like, for the particles, and then they're going to oscillate around that center. I expand in Taylor series the u here, right? So you get first a term which depends only on time, and then you get this nonlinear term which matches this x2. So to leading order, x1 just matches u, which you can integrate. It's a periodic function with zero mean. So that gives you some bounded displacement, but then to next order in x2, you get this famous Stokes drift. You get the fact that there is a quadratic motion given by this correlation between the gradient of the velocity and the linear part of the of the flow, so the perturbation. Okay, so this is why material, for instance, gets carried by surface waves, right? So the Stokes drift takes it away. Okay, so this is to show that the simplest mean, which is the Eulerian mean, is not necessarily the best one, because it doesn't keep track of the trajectories of particles. So Andrews and McIntyre, following various people like Brotherton and Grimshaw and Soward, developed this GLM theory. So the idea there is that you do an averaging following particle trajectory, so following at fixed particles. So if you consider a single particle, I label it by A, right? So A is, say, the initial condition for this particle. You split the position of this particle at time t between a mean position, depending on the particle, and then a displacement which you don't refer to the particle itself, but to its mean position. Right? So the mean position of a particle is equivalent to a label. Each label has a mean. Okay, so that's the idea here, is that you decompose the motion into the mean, which somehow, in this example, would be an average over the fast oscillation, and then a small perturbation. Yeah, so many particles will have the same mean. That's right. I mean, the particle position, my notation later will be a bit clearer. There will be an ensemble of perturbations, but a single mean, right? So once you average, you reduce the dimension of the system from an ensemble of trajectories to a single one. Okay, so how do you define then what is the mean? Well, you just require that the average of this guy over many realizations, for instance, in this instance, many phase shifts along the orbit, the average be zero. Okay. So when you do that, that gives you a definition for the mean, which surprisingly doesn't appear in the literature. It's just too simple. The original derivation of Andrews and McIntyre is very sort of implicit, but you can write this actually, that the mean position at fixed label is just the mean at fixed label, right? And then you differentiate this with respect to time. That tells you what the velocity of the mean flow is. Yeah.
So if I have a single numerical simulation, for instance, with oscillatory motion and mean flow, can I extract this x and xi, or do I necessarily
so you have to decide what you mean by your mean. But for instance, you could do a mean over a short time scale, or an intermediate time scale between the fast time scale of the motion and the slow time scale. So the kind of mean which Raf was talking about this morning. Okay, so if you just differentiate this, then it tells you that the velocity of that particle A, which when we write a velocity field, we refer it to the kind of current position, is given by this. Okay, so it's the average of the velocity at the displaced position. So really keeping track of the particle position. That's a Lagrangian mean. Now I won't show you the details, but it turns out that you can write equations for this Lagrangian mean velocity, which satisfy more or less the principles I showed in the previous slide. In particular, the equations are sort of nice looking. Certainly the vorticity equation that you get is very simple. The momentum equation that you get by taking this kind of average of the momentum equation is not so nice. Okay, so it's a kind of general rule that GLM is tremendously useful when you deal with vorticity, and so it's very useful for balanced flow, which are controlled entirely by vorticity. Okay, so I've shown you GLM and everything looks fine. In fact, if you start thinking about it, it has a major flaw, which is that it's completely coordinate dependent. So it's been cooked up in Rn, in an Euclidean space, and you can ask, what does it mean in a coordinate independent way, and you will quickly realize that it has no meaning, right? So I wrote here the 3 key equations of GLM, and none of them make sense, intrinsic sense. Okay, so why is that? Well, because we're making this addition here of a displaced position, of a mean position and displaced position. These are really positions in space, maybe on a manifold, on a sphere. You cannot add positions, right? They are not linear objects. There is no addition. So this works when you, in Rn, where you think of positions having vectors and you can add vectors, but on a general manifold, there's no way you can do this. Similarly here, you're averaging vectors at different positions. Averaging is adding vectors. But you know that you're not supposed to add vectors living in different tangent planes, right? On a sphere, different points have different tangent planes. The vectors live in their own lives. They're not supposed to be added. Okay, so this does it using the fact that it's cooked up for Rn. And similarly here, we're taking the mean of really a position, which doesn't make geometric sense. Okay, so this seems a cheap point to make. However, this has some sort of a damaging effect. So the first one is that if you start working on a manifold, say a sphere, you'll find that even though the trajectories you are averaging over are all on the sphere, the mean trajectory leaves the sphere. Okay, that's simply because you start adding vectors, 2 vectors tangent to the sphere. If you add them, you get something which is not tangent to the sphere, right? So that's not so good. And the other thing which is slightly annoying is that even if you start with flows which are incompressible, the Lagrangian mean flow is compressible. Okay, and that's because you haven't really, well, you do this construction ignoring the fact that you should really live entirely in the world of incompressible velocity fields. Okay, so the idea we had is to try a geometric approach, trying to cook up a theory to build an analog of GLM in a way which is coordinate independent. So one motivation is that the results will be valid on a manifold. That's not so exciting, perhaps. Another motivation is the fact that we are going to be able to see when we make choices which are coordinate dependent and trying to avoid those. And then the third one, which is more debatable, is that it makes GLM easy. I'll leave you to decide this. Okay, so now I need a bit of differential geometry. It's kind of coordinate-free differential geometry. So let me introduce just my notation and a few things. So we forget this sometimes, that the main object in fluid dynamics is not the velocity field. It's really the flow map, right? So the flow map, this phi, is what takes an initial condition to the position at time t. Okay, so it maps the label here A to the current position at time t. And I find that the GLM formalism kind of mixes flow maps and positions. So I'm going to be careful and only play with flow map as my main object. And then once you have a flow map, you can differentiate it, and that defines the velocity field for you, right? And so there's this kind of miracle of fluid dynamics that you can write equations only for the velocity field, but in the background there's always this flow map which you are interested in if you want to follow particles, know where they go. So my notation also, I'm going to distinguish it from GLM. I'm going to use lower cases for everything. So x is a point on the manifold, and then also I'll drop the time dependence, the explicit time dependence of my flow map, and in fact of anything else. Okay, so all the fields depend on time. Now in this business, you need a few tools of differential geometry. The main ones will be the push forward, the pull back, and the lead derivative. So let me explain what is the push forward of an object. Let's start with a vector by a map. So here's my manifold, and here's a point, and here's a vector at that point. So it lives on the tangent plane. Now you can think of a vector as being a little displacement between two nearby points, right? That's a natural definition. So you want to know, okay, so you know how to move points about using the map. So how do you move vectors about, which is what the push forward is all about? Well, it's easy. You take two nearby points defining, well, essentially tangent to the vector. You move those 2 points with your map. That gives you 2 new points, and you draw the tangent vector there. Okay, so it's a completely natural operation. If you know how to move points, you know how to move vectors. Then you may want to move also things backwards.
I have a question.
Yep.
So the map maps always into the manifold. The flow always maps.
Yes, I
into
will use a simple
by
geometry.
assumption.
Yes, and I will use a simple geometry where the manifold is fixed. Okay, so I'm not doing free surface flows, for instance, but one could. Okay, so the push forward is indicated by the star downstairs, and then the star upstairs is the pull back, where you move things with the inverse of the flow. Okay, so you can move things about on manifold in a very, very simple way. And then a sort of infinitesimal version of the push forward is the Lie derivative. So you take this is when you have a vector field, so you know your manifold is covered by little arrows, right? You take you go a certain distance away from the original point, you look at what the vector field is like there, you bring it back to the original point, and you differentiate. Okay, so this is, for scalars, this will amount to material derivative, and this is really the proper extension of material derivative to objects like vectors, and we will deal with more complicated ones. Okay, so this is a thing which just crops up very naturally. Now, I'm going to deal completely with incompressible fluids. And so in this case, I mean, what you have to understand is that the configuration space of fluid dynamics is the space of all the maps here, the flow maps, or diffeomorphism, because they are smooth and invertible, which preserve volume, right? So this is really if you remember classical mechanics, you have a configuration space, which is where the QIs live, right? Well, here the equivalent is this infinite dimensional space of volume preserving diffeomorphism or maps. And it also forms a group, because if you give me 2 maps, I can just compose them, right? So I can send a particle first with the first map, and then further away with the second map. Yep. Yep.
Where does U? Oh, sorry. I'm just.
Yeah. Okay. So
where's the U in the Lie derivative?
Yeah. So phi and u are related in this way. So u is the velocity corresponding to phi.
Okay. Thanks.
Okay. So also what I'll do for my notation is that since I'm thinking about really having an ensemble of flow, this is the usual GLM setup, I'm going to make this explicit, saying that someone is giving me not a single flow map, but an ensemble of flow maps, and alpha here will label all objects which depend on this ensemble. Okay, so you can think of alpha taking a few integer values, so someone gives you 6 flows, and then wants a theory about the mean of those 6 flows. You can think about having a family of periodic solutions, for instance, and then you make an ensemble of solutions by just shifting the phase a bit. Okay, so this is an example of a fast time, say a fast time wave, where just by shifting time a little bit, the fast time a little bit, you get another solution. So generally it's a family solution. You can also think of alpha as denoting realization of a random set of flow maps. So someone can give you a probability for each flow map. You have speaking French again, you have a bag full of flow maps, and then you can draw flow maps from this bag. Okay, so once you have such an ensemble, there's natural averaging for quantities which are linear objects, like vectors, right? So it makes perfect sense to average vectors, because you can just sum them, or vector fields, sum them at fixed location. So that defines a mean, or if it's a continuous variable, you just do the integral. So now there are 2 things which we need to do. One is to define what we mean by the mean flow map. So we given an ensemble, can we cook up a mean? That's the first part. And then the other one is, given a mean flow map, can we find equations governing the dynamics of this flow map? And so I'll start with 2, because one of the key messages here is that many properties of the equations that you get don't depend on the details of the flow map. Okay, so I'll start deriving equations, assuming that someone gives me a recipe for, given an ensemble of flows, finding the mean flow map, and then after that I'll explain how you can define the mean.
Sorry, you went a bit too fast for me. Can you say again what the flow maps, your ensemble of flow
so
maps
here,
are? Yeah, yeah.
So if you imagine that you have periodic solutions which are slowly modulated, so they will be periodic in this variable. So this would be, I mean, it's really corresponding to my my picture here. So you imagine a solution which oscillates rapidly and then drifts slowly. Then in a kind of multi-scale setup, you would write it like so, where this is periodic. Okay, and then you can just cook up an ensemble by just shifting the fast time parameter, so just a phase shift. So you just take different phases of your wave. Okay, so let's try to find equations for the mean map. Okay, so the first step is to decompose the map initialization into a composition of the mean map followed by the perturbation map, right? So this is the equivalent of what GLM does as an addition, which I complain about. It really should be a composition. So what this means is that here's my manifold. If you think about a point, here I have 3 flow maps in my ensemble, 1, 2, 3, and I just say that this point X is going to be sent first to the mean position, the same for the 3 realization, and then a perturbation. Okay, so you can think of it like that. So the way those maps act as a single point. It's also useful to think of this in the space of maps, the space of volume preserving diffeomorphism. There, a map is just a point, right? And so I'm just decomposing these 3 points into a mean, and then another map which sends to the perturbed state. Okay, so it's sort of helpful to think a bit about the map as a whole object rather than its action on each of the points of the manifold. Okay, so we need a good definition of the mean, so I'll say later what are possible definitions. So good here just means that if you have an ensemble of flow maps, well, first, I mean, they somehow need not to meander too far from the identity, right? So you imagine that to make an average of some objects in a nonlinear world, you need kind of local behavior. You need those objects not to take you too far away. I mean, an example is if you want to average points on a sphere, you need those points to be kind of on the same side of the sphere, otherwise it becomes a bit difficult. Okay, so I'll assume implicitly that my perturbation maps are not too far from the identity, right? So although this is not by means of small parameters, so it's just a kind of local requirement. And then the second thing, so what you imagine is that the flow map somehow is in the middle of the flow maps. The mean flow map is in the middle of the flow maps for each realization. And if you think about this, what this requires is really you should define your mean flow map in terms of flow maps, not in terms of the velocity field. Essentially, if you define a mean velocity field, it's going to be very hard to control where the map goes because 2 nearby velocity fields after a while give you very different flow maps. Okay, so you want a definition which is based on the map itself, yeah?
In what sense should it be close?
Well, I mean, I'm not an analyst, but it's a local behavior, close enough for the theory to work.
And, yeah, close enough in what sense?
Well, I don't know that, right? I mean, I can imagine that it will depend on the mean, but do you want a Sobolev norm of some kind or something? So you can define a notion of distance between flow maps. We'll see some actually, and then you just ask this distance not to be too large. Okay, so the idea here is that someone gives me a good definition for a flow map, and then the mean velocity that goes with it is simply its time derivative, right? So you just differentiate in time and cook up the corresponding vector field. And what's important is that when you do this, the mean velocity, which I just denote by u bar, is not the Eulerian mean velocity, right? Because it comes from a process which I haven't told you about, which how to define the flow map. So there's no connection between this and the standard average at fixed location. Okay. No, I mean the reason I introduced the machinery of things like the push forward is because that is how you do kind of calculus in this setup. So what you want to write down is an equation for this mean velocity and the perturbation velocity. So you just take the time derivative of this and you apply the chain rule, and then it takes this form. So it gives you kind of perturbation velocity, the push forward of the mean velocity, and that's equal to the full velocity. And from this equation, if you know what u bar is, then you know what the perturbation maps will be. You can just solve for those, or conversely, if you have some constraint on the flow maps, on the perturbation flow maps, then can define for you what U is. Okay, so we want to average the fluid equations. So first I'm going to play only with the Euler equations for incompressible fluids, right? But we can do better. You'll see a bit of that. So the first thing to do is to write them in the right way. So I guess like me, you've been unfortunate and people have taught you that this is how you write the fluid mechanics equations, right, with the U dot grad. This is not the most most useful way of doing this. So here is a more useful way. You first add on both sides, you add the gradient of U squared over 2, you add, and then you multiply by dx, okay, and then you can just rewrite this as this, where you understand that d by dt of dx is just du, right? So d by dt of dx is du, and then that's just ux dx plus uy dy, and then vx dx plus vy dy. Okay, so that's just an alternative way of writing the equation. You agree with me that, and so this pi here is just a substitute for the pressure, right? So then you see this object arises naturally, u dot dx, which you recognize as being the thing that you stick in Kelvin circulation, right? When you integrate u over contour, you have this u dot dx. So let's call this object as a whole. Let's call it the momentum, not as in rho times u, but momentum as in conjugate momentum from Hamiltonian mechanics. So this is what it looks like in the Euclidean world we started with. Okay, in general, it's the object which you get by taking the velocity field and then using the metric, so my manifold has a metric, to turn it into the dual object. Okay, so this is the operation of lowering indices in coordinates. Okay, so a metric is just an object, you give it two vectors and it gives you the dot product between those two, it just gives you a number. This definition here says that if you, okay, so the one form here is a dual to vectors, that is, you can pair one forms with vectors and you get a number. Okay, so these are the linear maps on vectors. So if you have a vector and one form, you pair them together, and what you get is just what looks like a dot product, but the forms and the vectors live in different spaces, right? So this is Paola has a question about covariant and contravariant vectors. So the one forms are the covariant vectors, and the vectors are the contravariant vectors. Okay, and so if you want to do things in coordinates, then my nu will have the little bit. So if I have coordinates xi, it will take this form. So these are the components. There is a lower index for it, and it's related to the velocity here using the metric tensor to lower the indices. Okay. So the point is that it's kind of more natural object because it crops up in here. And so in terms of this momentum, you can write the Euler equations. So those equations, you can write them on any manifold in this rather elegant way, which says that the rate of change of this momentum one form following the flow, so there is a local rate of change, and then there is a change, because of advection by velocity. Advection here being kind of translated by the proper Lie derivative is the gradient of something. Okay, so d is just the equivalent of the gradient. So we have this, and we have the divergence of u. Okay, so I write this. I think it's pretty, but why is it so good? So well, one thing is that you can write this immediately using the definition of the Lie derivative as this thing. Okay, so it tells you how the momentum, this momentum one form, when pulled back by the flow, how it changes. And this is just Kelvin circulation theorem, really, because if you okay, so what is Kelvin circulation theorem? So you'll remember I said this is the object that you get in the integral, right? U dot dx. So you should integrate this one form on a contour C0 which moves with the flow. So I just take the map. I just apply the map to the contour. So what you can do is that you can pull back this equation by the flow. Okay, so if you this was the push forward of the curve. If you pull it back, now you have a curve which is fixed. But now you have the pullback of the vector. But we've just been told that the time derivative of this is just an exact derivative which integrates to 0 on a closed curve, right? So you get 0. So this form is really just Kelvin circulation theorem in disguise. And for more complicated fluids for which circulation is not conserved, you still have the core of the fact that the circulation is going to change, but only due to some subtle effects like stratification, for instance. Okay, so that's one reason why it's a good way of writing things. Another one is because of Arnold and others, which said that you can think of fluid dynamics as being geodesic motion. So there is a notion of distance between two diffeomorphisms. This is answering the question partly. So the notion of distance is that you take two diffeomorphisms, you try to join them by as many flows as you can, and then you find a flow which leads to the shortest distance, and the distance here is the time integrated, volume integrated kinetic energy, or time integrated kinetic energy. So you try various flows that gives you various velocities, you calculate the corresponding kinetic energy, you integrate in time, and then Arnold's claim, which is it's not too hard to check, is that the equations of the earlier equations arise as for the minimum trajectory. Okay, and the point I'm trying to make is that if you do this calculation, the equations fall exactly in this form and not in the form we are more familiar with. Okay, and then finally, so the generalization of the standard way of writing the earlier equations to manifolds, you can also write it in this way using the covariant derivative. So if you know about it, you know it's a bit complicated, and if you don't, then you don't want to know about it. So this looks harmless, but in fact it's a complicated object. Okay, so arguably this is a much cleaner form.
So pi is a sort of like Lagrange multiplier and something.
Yeah, that's right. So the pressure crops up when you. So here I constrain my flow maps to live in this world of incompressible, of volume preserving maps. So you have to put in a Lagrange multiplier, and that's how you get the pressure. Okay, so now I can just try to average the equations of motion written in this form. And because it's the right form, then everything is really easy. Okay, so I have here, so I've now written the Euler equations for each flow alpha. What I'm going to do is I'm going to pull back those equations from the disturbed configuration to the mean configuration. And in this world, there's only one way of pulling things back, and that's using the pullback with the perturbation map. Okay, so I do this, and then there's a little miracle, which is that when you do this, so you have here advection, if you like, by each of the flow. Well, first, so the pullback operation is very natural in the sense that the pullback of such an object becomes the lead derivative of the pullback applied to the pullback. Okay, so everything sort of is nice. So the upshot is that you get, once you average, you get that this quantity, so the average pullback of the momentum is simply moving with the mean flow. Okay, with some sort of derivative. So it makes perfect sense to define this as the Lagrangian mean momentum, because it satisfies this very simple equation. So what has happened here, right, which is something which is recurrent, is that when you start with those equations, there is a very close connection between the momentum, which is being advected, and the velocity, which is doing the advection, right, because they are just dual of one another using the metric. Once you do this averaging, you've somehow broken the connection. So now this object and this one are not so closely connected. One comes from the definition of the mean flow, the other one comes from this average in this generalized Lagrangian mean sense. Okay, but because the form is so simple, I can repeat the derivation of Kelvin circulation theorem, and I know that it will be satisfied for the mean velocity. And again, the contour will move with the mean map, so the velocity is the mean velocity, and the integrand now is something different. Well, no, you don't, because you have to say something about the perturbation. So now, I mean, this is your question. All the business of wave mean for interaction is now encoded in the relationship between the advecting velocity and the advected one form. Okay, and then you have to tell me about the physics of your problem, and then I can say something. And so a way of making progress, we've seen this in Ralph's talk this morning, is to define things, right, and at some point claim they're constant. So here I define the pseudo momentum as being the difference between those two objects. So this is a vector, this is a one form, so I need to first turn my vector into one form to subtract things which have the same nature. But so what you can say is that wave mean for interaction is entirely encoded in this P. And this is related to the same P we've seen in Oliver Büller's talk. So what you need is some sort of closure to express P in terms of the mean variables, or maybe its own equation. So there is a kind of school of people who amuse themselves devising simple models for this P and coming up with things like the alpha Euler equation, for those who know this. Other people work harder, and then they try to describe the dynamics of perturbation to know what this P looks like, for instance, for linear waves. Okay, and so one more thing is that, so I was led naturally to this definition of the Lagrangian mean momentum. This is a natural definition of the Lagrangian mean of anything. So if you give me any quantity, there's a natural way of taking the mean, which is to put it, so any object here, the dots, put it back using the perturbation maps, and then average. Okay, so the only, and so for instance, when we play with the Buoyancy equations, there is a buoyancy. The natural mean buoyancy is the Lagrangian mean buoyancy in this case. Same thing for when you have a magnetic field. The only unfortunate thing is that the mean velocity is not the Lagrangian mean velocity in this sense. Okay, so it comes from a different construction, which is the definition of the mean flow. Okay, so this mean flow, how do I define it? Right, so what we really have to do is to try to define the mean of a very nonlinear object. So we are given a bunch of maps, flow maps, diffeomorphism, which preserve volume. How on earth are we going to define the mean? So you realize it's a difficult problem, right? It's like if I give you 5 points on a sphere, define a mean of those points, you may come with your own solution, but not everybody will agree that is the right solution. You can try to take the mean of the longitude and latitude, but that's not a good idea because it will depend on where you put your axis. So you want to find something more intrinsic. So here, to find something more intrinsic, we can use two things. So this manifold, this group of volume preserving diffeomorphism is a group. So there's natural operation to compose, in this case, compose maps, and it's also Riemannian. I've shown you a distance, the one used by Arnold. Okay, so here I want to discuss, maybe it's a bit ambitious, 4 different definitions. One is a kind of desperate attempt to recover GLM, the classical one, but now in a way which is coordinate independent, so that at least in Euclidean space we agree. Another one is a kind of slight variation which brings in optimal transport. The third one is, in principle, the most beautiful, but I'm not, it's a bit difficult. And the fourth one is something which in fact is very practical, due to Sword and Robert, this little GLM. Okay, so let me explain the 4 definitions, and they all follow the same scheme, which is, well, for the first 3 anyway, to define a mean by some sort of minimization argument. So what do I say? Okay, so on this manifold, I have a notion of distance, right? Because I have a metric, so I can measure distance between points by following shortest path. And so what I do is that for each point I calculate the distance between, so I have a kind of a test diffeomorphism, I have the ensemble, so I calculate the distance of each point, take the square, and then integrate, this is the volume element, integrate over the whole manifold, and then I minimize over diffeomorphism. Right, okay, so I'm trying to find a diffeomorphism whose sum of square distance, well, for which the sum of the square distance of each point is minimized. Now, this is easy to write. This is much harder to compute, because I mean, when you want to calculate distance over a manifold, this object here, you really need to find the shortest path, right? In Euclidean space, we know there's a straight line. Otherwise, you have to work hard. So how do you do that? Well, the easiest way is to think of. So I have my mean. For the moment, I don't know where it is. I'm going to try to kind of move it about, hoping to find a minimum. So the way to do this is that you parameterize the the geodesics here, so the shortest path, right? And the way to parameterize them is in terms of the vector the vector field. Okay, so at each point here, I have a vector that tells me how to evolve my path.
Excuse me.
Yeah.
Is there a reason why we choose the phi from all diffeomorphisms, and before we had S-diff, which was
Well,
the
okay, so
volume-preserving
this is a very
ones?
good point. So the next slide will have an S. So at the moment, I'm not restricting myself to volume-preserving diffeomorphism. That's because I want to recover GLM, and I know GLM doesn't conserve volume. Okay, so the mean flow in GLM will not conserve volume. So very good observation. I'll fix that in next slide. So, right, so those vector fields, okay, so I should explain. We know fixed time, right? Someone gives you at a fixed time this ensemble of flow maps, and I'm going to construct them following a flow of a kind of fictitious time, right? So this is the fictitious time is just a parameter along this curve in the group of diffeomorphism, not volume preserving. So it's more or less, well, okay. So those vector fields satisfy just a pressureless fluid equation, right? So this is just the dynamics of a gas where there is no interaction between particles; they just each follow the shortest path on the manifold. And then, so what's important is that the condition of minimization, when you start moving this mean flow about, gives you a condition on the vector field at the origin. Okay, so the mean of them is 0. So this is reminiscent of what's happening in GLM for those who know this. So you can't work out this distance right off the bat in general. What you can do is to do perturbative calculation. So if you start thinking that your perturbation maps are not too far from the identity, you can expand things in power series. And so when you do the calculation, what you find is, so this Q is this vector field generating the shortest path. It has 0 mean, and then the mean at second order is given by this covariant derivative. And for those who know GLM, I've translated everything in terms of constraint on the perturbation map itself, this object, which I also expand, right? So to leading order is the identity, and then a small perturbation still. To leading order, you get that the perturbation map has 0 average. This is what GLM tells you. To the next order, you get this correction here involving the Christoffel symbol, which vanishes on in Rn, right? So you recover GLM.
Sorry, just at the beginning, I didn't get why you integrate on omega. I mean,
so omega is just a volume element, dx, dy, dz.
So d2 is.
So you take each point, you see where it's going to be mapped, you measure the distance on the manifold, and then you integrate over the whole manifold, the square distance.
So the manifold you are integrating on is diff of.
No, the manifolds. This is all on M.
Right. Okay.
Right.
You are integrating on M.
That's
Yeah,
right.
Okay.
Yes.
Okay. Thank you.
And then I'm looking for the minimizer, so the best choice of the map there. Okay. And so as has been commented, this, of course, this is GLM, doesn't respect volume preservation, but it's a very cheap thing to change this by just adding the S here, which means volume preservation. So you can carry on the same calculation, and what you find is that the constraint, which was that the mean of the kind of fictitious velocity fields be 0, has now turned into that this mean should be a gradient of some function, and you pick the function to ensure volume preservation. Okay, and that's, I mean, this is, if you know about optimal transportation, this is what arises there, because I'm just doing that actually. So again, I can calculate things order by order, and yeah, I have interesting results in the sense that now what I had here, which had no constraint to do with divergence freeness, now has been replaced by this way. It's the same quantity which I now project on the space of divergence free vector fields. Okay, so I just kind of enforce by hand the divergence free condition. So that's a kind of small variation on GLM. The price to pay is that things get a bit messy in terms of the perturbation maps. Right? Okay, so then my favorite is this one, where you change the notion of distance. So Arnold gave us a nice version of what the distance is between two diffeomorphisms, and let's use that one. Okay, so this is the one. Yeah, so how does this work? So we're measuring distance between two diffeomorphisms by doing what? Well, we try all the paths joining them in the space of diffeomorphisms. So we try all the fluid flows, if you like, which join those two diffeomorphisms. And for each of them, so gamma here is the diffeomorphism parameterized by this fictitious time. For each of them, we calculate the kinetic energy and try to minimize this, right? So this is the one which gives the Euler equations. So you can just use this and then say, okay, my mean flow will be minimizing the sum of the square distances. Okay, so compared to the other two examples, I've just changed my notion of distance to one which is it's more intrinsic, right? Because this one only the final map was volume preserving. If I think about paths, they were leaving the group of diffeomorphism and then getting back into it. These ones, they stay in among volume preserving diffeomorphism all the time. So the upshot is that the paths satisfy the Euler equation written here with a projection to eliminate the pressure to ensure divergence freeness, and then with simple conditions. Okay, and again you can work things out. And then the final example is a little bit different in that there is no functional to minimize. All it says, so this is one due to Soward and Robert. All that it says is that it says, okay, let me try to get to my perturbed diffeomorphism from the main part, following a vector field which is not time independent or S independent, which is a fixed vector field. Okay, so that's one way of writing this is that you write the perturbation map as the exponential of a vector field. So exponential means solve the differential equation going with this vector field for time 1. Right? So what is nice about this is that it turns this nonlinear object, which you cannot average meaningfully, into a linear object because it's a vector field which you can average naturally. And so what would be, this is 0 on average, or maybe the identity on average for GLM is turned into, this should have a 0 average, and that makes perfect sense on any manifold. Okay, this is quite nice. The kind of drawback of this is that you cannot write this in general. In fact, you can almost never write it. That is, if I give you a flow map, there is no time independent vector field which constructs this flow map as time 1, right? Which intuitively is probably clear. I mean, a time dependent vector field reaches places in flow maps which a time independent vector field doesn't reach. Okay, so, but I mean, if we work at a perturbative level, this is not much of an obstacle, and this definition is quite nice because it gives rise to very simple conditions for the vector field. All the averages are 0, and things which are not too bad for standard GLM. Okay, so essentially standard GLM would have 0 here, but would have a complicated expression here, and then depending on whether you prefer to play with Q or psi, then things are complicated in one formalism or complicated in the other. Okay, so it becomes really a matter of taste. Yeah. Okay, so let me just go through an application at least, which is.
Can you explain again the sorry, I missed part of, so locally in time it's okay? I mean, to write
yeah, so you can essentially say in 2D, for instance, all 2D time independent vector fields give you integrable flows, right? That's only a small subset of the flow maps that you can get. Right, so it's going to be, it's not going to be even true locally actually. So it's going to be true order by order, but the series that you get are not convergent.
Order by order in
well, if you think that you're working locally, then you have a small parameter, then you can do calculations perturbatively, but the object itself doesn't exist. Okay, so the simplest example to show that's the case is that if you have a time independent vector field, then there are no isolated periodic points, because every time you have a periodic point, then the whole orbit is made up of periodic points, right? So if I give you a flow map which has a periodic point which is isolated, then it cannot come from a time independent vector field. But I don't think it has much impact in practice. Well, not sure what practice means, but right. So here's an example which is related to what we've seen, and it's to study the effect of waves, internal waves or inertial gravity waves, on mean flows described by the Buoyancy equation. So I start by writing the 3D Buoyancy equation in the kind of the geometric language. So so it's pretty much as before. So I still decorate with an alpha to indicate that I have a bunch of flows. That's my momentum. It's not the absolute momentum because I'm in the rotating frame. I need to add to the momentum this Coriolis term. Okay, so that's, trust me, when you plug it in here, it will give you the right Coriolis effect. It's very nice, right? It's very simple. It's much simpler than the original equations. Yeah. So we have this pressure-like term. And then this is the buoyancy term, right? And then the dz here is the form version of the vertical vector. And then, so this is momentum equation. We have an equation for the buoyancy or the temperature, which is just advection by the flow, and then the flow is diversion free. So, I mean, the power of this kind of language is the fact that, for instance, deriving PV conservation is a one-line calculation. You act on this with the differential external derivative, which is like a curl operation. That kills this term. And then you act on this with also the differential. You take, so the wedge product is some sort of extension of the cross product. And there you go. This is a version of potential vorticity conservation. Okay, so I want to apply this to a system in which I'm going to assume that the mean flow is balanced. So if I know the mean PV, I know everything about this flow. So I don't have to worry about averaging those various equations. All that I care about is this one. And this one averages very, very nicely because it just takes the straightforward form. So the velocity field becomes the average velocity field. The momentum becomes the average momentum. And then if I assume that the buoyancy in each flow is obtained from the same initial buoyancy field by different maps, then I have this very simple, I mean, I don't have the mean of the two quantities, I have even the mean of each. Okay, so it's a super simple expression. And now we can do some work, assuming, as I will do, that we have a small, I guess there should be an epsilon here and epsilon square here. So I'm going to assume that at leading order I just have waves on a resting basic state. And then what I'm interested in is what is happening at the next order. Is there a mean flow which is generated? What does it look like? So then, so those waves are fast compared to the geometrically balanced flow. So I can take my average to be over fast time. You'll find when you sort of unpack those equations, you'll find geostrophic balance. So I mean, it's a sort of an interesting fact that what's coming in the Coriolis term is always the velocity, not the momentum. So I can introduce a mean stream function. Now I have the mean momentum, which will be given by the velocity written here as a one form, and then there will be some wave terms, which I can work out with any of the definitions of the mean flow that I've shown. And so when the settles, everything has to be controlled by potential vorticity conservation in the means. And so I get this Lagrangian mean PV equation and a relationship between, I mean, again, between the advected quantity here, the PV, and the advecting field, which involves the effect of the wave. So there's the effect of the pseudo momentum will be a way of putting it. And so this is something which people in the audience will recognize. This is the form of the potential vorticity. So there is a term here, I'm forgetting the DZZ here, which is, or the DZDZ. So this term is a normal potential vorticity inversion equation. But then I have those terms which depend on the quantity subscript 1, which are the waves. Okay, so this is a potential vorticity which is associated with the waves. So the waves do contribute to the dynamics by changing the relationship between the potential vorticity and the field which advects them. Right? And the fortunate fact, if you like, is that regardless of how I define my mean flow, I always get to the same equation. But it's sort of interesting to see that you get to it by different means. Okay, so in particular, when you do this in GLM, which was the original derivation, you have to fiddle with density because your mean flow does not preserve density. So writing this is a bit fishy, really. So you have to do things with corrections and so on. If I use one of the three formalisms for which the mean flow is diversion free, then I don't have to worry about that. Yeah. And at the end, you get the same equation because you're describing the same physical system. Right? Okay, so just to conclude, so the idea here was to kind of revisit the GLM theory to fix what I found were kind of unpleasant features. Michael McIntyre and I have had discussions about how unpleasant they are. It's a matter of taste a bit. But so the benefits is that we can obtain an incompressible mean flow. At least we can use a manifold like the sphere and be sure that the mean flow stays on the manifold. And then the whole thing is coordinate independent. What this shows is that there's a sort of natural definition of the Lagrangian mean, which is pulling back by the velocity, by the perturbation map and then averaging. Unfortunately, the Lagrangian mean velocity of GLM is not of this type. And then, yeah, so I showed several definitions of the mean flow. They all, in this perturbative context, they all a small amount apart, which is why the dynamics that I see is the same, because to leading order, the mean flow is just in the middle of all those perturbed flows. Yeah, so the mean circulation theorem kind of comes with the procedure, because it's all based on writing equations in a form which is Kelvin circulation friendly. And so we have to worry about the connection between the Lagrangian mean momentum and the mean velocity, and that tells us what the action of the waves are. And then, yeah, the last comment is cryptic, so I'll drop it. Okay.
Thank you, Jacques.
Jacques, I've just gotten used to the idea that Stokes drift is compressible. If you go back to, it must have been on your first slide, I guess, you had the standard formula for Stokes drift. And if I calculate the divergence of the Stokes drift velocity, it's not necessarily zero, I think. I must have even, I think it was really slide 1.
That may be so, but I mean, so the question is, what is a Stokes drift? And I guess to me the Stokes drift is the difference between, Lagrangian velocity and Eulerian velocity, so I guess I would get an incompressible Stokes drift.
So that must imply a modification of this formula.
Yes, that's right. That is right. Yeah. In fact, I mean, so this formula, you can tell there's something not quite right, because this is not a geometric object in the least, right? And the true formula is, in my formalism, the formula becomes the Lie derivative of the velocity with respect to this guy. And so Lie derivatives preserve, so if you take two divergence-free vector fields, the Lie derivative is also divergence-free. But then I don't know, it's a good question what it means in terms of this calculation. It has to do with the definition of the mean, I guess. Yeah, I probably cannot enforce this to all orders. I will have a mean correction to the flow. But I mean, one comment is that so Bill, you're happy if you've got used to the idea that the Stokes drift is divergent, but I mean it should be a shock, right? I mean we're living in a world of divergence-free velocity field, of volume-preserving maps. There's just no right to live that world ever.
Well, the way I reconciled myself to it was realizing that the Stokes drift velocity for surface gravity waves had vorticities in a completely irrotational flow.
Right.
So I figured if you could produce vorticity out of averaging, there's nothing wrong with producing divergence.
Well, except you can do better and have an averaging which avoids that.
So you said you cannot use GLM on a sphere on the original formulation. And I was wondering if the wave displacement is small as compared to the radius, say, of the sphere, are you approximately fine? Or because locally it must be approximately fine on the tangent plane.
I mean, what you can do if you want to use GLM, you can do it in coordinates, right? So if you use spherical coordinates, then you're fine. I mean, your mean flow will stay on the sphere, but the result that you get will depend on where you choose to put your axis. Right. So there is no, I mean, in GLM even, so you can either use GLM in the embedding Euclidean space, in which case you're going to have this problem of mean trajectories leaving the sphere, or you play with coordinates. in that case, there's nothing outside the sphere if you play with lambda phi.
Something that's been mysterious is, to a lot of people, I think, is what exactly pseudo-momentum is. And I was wondering if your theory provides a kind of a reinterpretation of...
Well, to an extent.
I know you wrote down the mathematical formula. But
yeah, so to an extent. I mean, I'm not sure what you ask, but it seems a good definition is that it's what makes the difference between the advected momentum and the advecting velocity field, right? Incidentally, I mean, so it's sort of instructive in general to think about models where you break this link between advecting field and advected quantity, and there's a recent paper by Terence Tao who plays that game where he uses more complicated relationships to try to see for which ones he can prove long-time existence of solutions to Euler-like equations. So he's playing that game too.
So have you actually used this formalism for stochastic problems? So for
No.
No?
No.
Do you think it may be useful?
Well, yes.
More question?
In your application, you choose to start at with a wave at order 1 and then the mean flow at order 2. What if there is a zeroth order mean flow?
Yeah, so we can do it. I vaguely consider it becomes complicated, but in principle, yeah, you can do that as well. But there was this community of people who have been a bit lazy, so I just carried on.
But then this, so the.
But it's interesting to have a mean flow linear order because then it brings in Doppler shift and interesting physics. And so, one of the beauties of GLM, this is what I try to convince Bill, I think, is the fact that if you do things order by order, you have to decide at the outset that you have such a scaling, whereas the GLM equations are valid even if there is a mean flow. It's just at some point when you want to write them down, it becomes simpler to ignore it. But the whole machinery works with a mean flow.
Hello? Oh, yes. It's not clear to me that it's necessary to use a Riemannian metric to define these things. You can use a Lorentzian or symplectic, and you can get other.
Well, so you need a metric, right? So fluid dynamics needs a metric, or in fact, maybe a pseudometric or something. Yeah, I mean, you want to, if you use
a metric, but why the Riemannian one?
Well, you can do anything, but if you want to get the Euler equations on a manifold, you need to tell me what the manifold is as a Riemannian manifold. But a kind of interesting observation, which is the fact that if you want to do this in the hydrostatic approximation, then it becomes just a matter of changing your metric to one which kind of drops the third component when you lower indices. Okay, so then it becomes, it's not a metric anymore because it's not positive, but positive definite.
So in the case of the Euler equation, the metrics actually come from Hamilton principle.
Well,
I mean the fact that you the Euler equation minimize this
yes, well,
quantity,
right.
it is the action actually that comes from Hamilton principle.
Yes.
So in this sense, you get a very natural way to.
Yes. So the manifold has a metric in the usual sense of giving you a distance between points on the manifold that induces a metric between diffeomorphism, and it turns out that this is the right one to use to get the Euler equation as geodesic flow on the group of diffeomorphism.
Okay, so thanks again.